Gauss'Law, spherical symmetry. A thin, uniformly charged spherical sphere with total charge Q. This one, very thin charge Q, with radius R. Okay. You want to find electric field at this point with radius R from the center. Okay. So what we do, we make a Gaussian surface as a sphere with the center overlap with this sphere. Okay. And that's very simple. Okay, very simple. This is total charge, there's total charge, that's what Q. And E, by symmetry reason, from following, the E is along the radius, okay? dA is along the radius. So this becomes E dot dA becomes EdA. By symmetry reason, E is constant, we take this E out, okay? And this integration dA is the surface area of the sphere, 4 pi r squared. So the E equal 1 over 4 pi epsilon Q over r squared. This r is larger than r. So it looks like this sphere can be treated as a point charge at the center. Okay, exact one. Yeah. Now, we want to find the charge electric field inside the sphere. What happened? Then we do make a Gaussian surface as a sphere overlap with this charge. Okay, and by symmetry reason, we will find all the E on this surface are the same. And unfortunately, inside this Gaussian surface, we don't have a charge. Okay, so finally, get the E equal to 0 when R is smaller than R. Now look at it. Here we use Gaussian law to prove the two shear theorems presented without a probe. A share of uniform charge attracts or repels a charged particle that is outside the sphere, as if all the sphere's charge were concentrated at the center of the sphere. The first part, outside. This is outside. Looks like hold the sphere as a point, okay, when R is larger than R. Now, this is a charged body, this is a sphere. Which calculate the attraction, we can treat this whole sphere uniformly distributed, okay, as a point charge located at its center. Okay, so this becomes a very simple question. 2 points, one is big Q, one is small Q, distance is R. Second part, a share of uniform charge exerts no electrostatic force on a charged particle that is located inside the sphere. Now, this is the uniform sphere. A charge inside the sphere, the force is 0. Okay. Now, let's make it further. It's not sphere, it's a sphere. A point charge Q inside a uniformly charged sphere, solid. Okay, the total uniform charge is Q. Okay, our small q is here. The distance r from its center. How we handle this one? We can divide this sphere into 2 parts, with the r as a border separation. Then look at this gray sphere, a little bit thick. Okay, this big sphere can be looked at as many small sphere, very thin sphere composed of this. Okay, and this cube is inside each sphere. In other words, all this sphere will not have any force on this cube from our theory. Okay, so forget this part. Then next one. This is a solid sphere with charge q prime. The q prime is smaller than q, is part of it. Okay, and we can look at this sphere is composed of a nest of a sphere with different r, and this q is outside all these sphere. Then, according to our theory, each sphere can be treated as a point at the center, and then this becomes 2 points. Okay, This is every shear some concentrate this one, so it becomes this point. The charge is Q prime. Hold the charge of this solid ball. Okay, we can treat it in this way. Right. Further, if this is not uniform distributed, okay, that's what we should. And then we want to find it has symmetry spherical. Okay, what does it mean? The charge density rho is a function of R. Okay, if we want to find the electric field at this point with distance R to the center, what we do, okay, any spherical symmetry charge distribution, such as that of the figure, can be constructed with a nest of concentrated spherical shears. For purposes of applying the two shear theorems, the volume charge density rule should have a uniform value for each shear, but need not be the same from shear to shear. That is, for the charge distribution as a whole, rho can vary, the density can vary, but only with R. Sim R, sim rho. Okay. The radial distance from the center R. We can then examine the effect of the charge distribution shear by shear. Now, if you want to find an electric field at this point with distance R, what we do, we make a Gaussian surface with the same center and passing through one radius R. Okay, yeah. Now, suppose the charge density rho is function of R, and that means the same R, you have same rho. So this is a spherical symmetry. And what we do, we think this is the E at this point equal to Q prime as a point at the center. What is Q prime? Q prime is the charge inside this Gaussian surface. Okay. So what we do, how we can find this one? Okay, we can suppose we have a small shear. The radius of the shear is R prime. The thickness is dr prime. Okay, and then the electric field produced this shear is equal to Q over R squared. So. Okay, and this total Q inside this sphere, we can do rho dV. This rho dV is this dV plus charge density, the charge, and we have R changed from 0 to big to small r. So this is total V. Okay, we can find this one. Depends on the function R prime. Okay, the dV is the shear 4 pi r prime squared the surface area times the thickness dr. This dV. This is the charge. And put charge together, we can find the E. This Q prime is the charge inside this Gaussian surface. Okay. Now, if you want to find a point outside this charge distribution here, R is larger than this R, then we found the auto charge, nothing to do with R, is also with R, because if small r larger than R, you don't have a charge. Okay? Yeah. So at this point, if charge density rho is constant, that's be much easier to do. So the Q prime equal to the rho times the volume. Okay, the volume. And the total charge is 4 pi r squared cubic over 3. So we take the ratio, we get the ratio is equal to r cubic ratio. Okay, and the E equal to Q prime of R squared. That's it, easy, right? And we put this one inside, and we get this one equal to Q over 4 pi epsilon R squared over R. Okay, actually, what I would like to say is Q over R squared, small r over big R, the ratio. Okay. This is a uniform charged field at R smaller r.